Hi, my friend. It's so good to have you here. So, here's the thing, if you want to build a mobile app for both Android and iOS, you have to first write for Android in Kotlin or Java and then do it all over again for iOS. You could write in Swift or Objective C, so that's double the work and double the pain, but that's all over now. So with React Native, you can just build your app in just one language, which is JavaScript, one code base, and boom, your app runs on both iOS and Android. And if you're already a web developer or you're familiar with React, that's such a great win. So, and the good part is that it actually renders as real native UI on both platforms, both iOS and Android. So this means your app uses the same native platform APIs. So that's pretty amazing, right? But this begs the question, how does React Native work? How does JavaScript code actually turn into native UI? So that's exactly what we are going to explore in this video, and let's dive in. Let's imagine you write a single code in React Native like this. It's just a simple function with a view and a text that says hello world. So what happens next? All your JavaScript code is bundled by Metro Bundler into a single file, basically to optimize performance. So this is similar to way Webpack works for web. So this bundle.js is then sent to the target device, and on the device, the native code runs directly on the device. So Objective-C or Java code runs directly on the device, while the JavaScript code runs inside a JavaScript virtual machine, for example, JavaScript core, or in the latest version, Amis. Now, the big challenge. These two words, they don't speak the same language. So how do they communicate? This is where the famous bridge comes in. So the JavaScript side can't directly manipulate the native UI component like the UI view or the view group. So the JavaScript has to send an instruction as serialized JSON messages through the bridge. So the native side receives these messages and deserializes it and calls the appropriate platform APIs to render the actual native component. I know it might sound a bit too much, so let's visualize this for better understanding. So let's say, for example, JS would be like, hey, create a view, add a text component that says hello world. So the JS sends this message as serialized JSON across the bridge, and the native side receives this message, deserializes it, and renders the hello world with the native API. So if, for example, we also render a button and the user interacts by tapping on the button, the native side sends message back through the bridge to the JavaScript. I hope we understand now. So it could send that, okay, blah blah blah, do something. So you can think of the bridge like a translator between two friends who speak different languages. It works, yeah, but it is asynchronous. So the JavaScript sends a message, it waits, and only after the native finish processing the whole information can the next step continue. So to keep things smooth, React Native spread the work across multiple threads. So we have the main thread, or we can call it the UI thread, the JavaScript thread, and the shadow thread. For context, a thread is the smallest unit of execution within a process. So the main UI thread handles everything the user sees and touches. So this is the same thread a fully native app would use for rendering the UI. The JavaScript thread, it runs the app's business logic. And for the shadow thread, since native doesn't really understand CSS, so it has to run layout calculations using an engine called Yoga. So Yoga computes the position, the margins, the layouts in the background. So the key idea here is that the main UI thread should stay free of heavy operation so that the app can feel responsive. So heavy lifting like business logic and layout is offloaded to the JavaScript and the shadow thread. So this is how React Native used to work, and it is known as the old architecture. At first glance, this bridge-based system, it seems fine. The JavaScript and the native side can communicate quickly through the asynchronous bridge. However, in scenarios where timing and precision are critical, this async communication can introduce significant problem. So, suppose we render, let's see an example. So suppose we render a tooltip based on the size and position of a view. So the code should look something like this. So now imagine a user moves this view across the screen every second. So by tapping on the screen. So let's see what happens. Let's visualize this. So the JavaScript side tells the native to create a view and place it at the top left. Okay, so once that's rendered, the native sends a confirmation back, for example, on layout. So we lay out this target at the top left. Then it sends a confirmation back on layout, and the layout, the JavaScript, that's when the JavaScript will calculate the tooltip position and then send another instruction to the native to update the UI. But by the time this update goes through, the user have already moved the view again. So it sends another message to the JavaScript that the top right was pressed. I hope you understand. Then the JavaScript triggers the function and sends an update message to the native to update the UI again. So these cycles go on and on and on. So because of this async behavior of the bridge, it results in the tooltip visibly jumping around instead of smoothly following the view. So in simple case, this might only cause a small flicker, but in complex scenario like animation, it becomes very critical because the lag introduced by the bridge can become a major problem. If we look at other example, for instance, when formatting input like credit card number, we want to insert a space every 4 digits for easy readability. So the user might briefly see 27201 with no space between the 0 and 1. So then after a few seconds, if you look carefully, there will be a space between 0 and 1. So another classic case is fast scrolling in a list view. So the native side may not know what to render in time. So when you scroll so fast, so it differs to that JavaScript. Meanwhile, we see blank items appear on the screen. So this results in visible gaps, and yeah, it's not good for the UI. So you see these jumps and delay can significantly affect user experience, especially in complex apps, so which may have a simultaneous updates. The async bridge becomes a problem. Plus the fact that each message has to serialize and deserialize, it consumes time and may lead to the main thread getting blocked. So as the performance demand increases, these limitations become more significant. So to address them, the React Native team had a major architectural redesign, and that's where we have the new architecture. So the biggest and the most important change is the removal of the asynchronous bridge, replacing it with a JavaScript interface, JSI. So this new bridgeless design, it allows JavaScript and native side to communicate synchronously, which is exactly what we really need to eliminate the delays and the bottleneck caused by serialization. But how does the JSI work? So at the core of this system is C++. So JSI is written in C++. So it exposes native Java Objective-C method and object to JavaScript to a construct called the host object. So JavaScript will hold a reference to this host object. It allows it to access methods and properties on the native side directly without serialization or any round trips needed. Okay, to explain what this host object is in simple terms, you can think of host objects like a remote control. So it's like a remote control for a native object. So JavaScript holds this remote control and can press any button, like call the method, can press any button like to call the method or read properties and directly on the native object without sending any message across the bridge. So there is no bridge here. I hope we get that. So another key component to the new architecture is Fabric. So Fabric is a new rendering system also written in C++. Because the old architecture relied on asynchronous bridge, handling multiple updates at the same time could cause the UI thread to get blocked and slow down the rendering. So Fabric solved this, and thanks to the JSI, Fabric can now measure and render the UI synchronously, reducing lag and making interaction feel instant. For example, the tooltip issue we saw earlier in the old architecture, it disappears with synchronous measurements. You can see the difference. Now it's moving synchronously. So another good thing about Fabric is that it also supports multi-priority scheduling. So which means that it can interrupt low priority tasks. For example, we make a network request. Normally waiting a few milliseconds for network requests doesn't halt, because normally we have to wait for a few seconds sometimes to handle urgent interaction like synchronous operation like scrolling, animation, where this millisecond actually counts, because if there are lags it becomes so less UX interesting. So we want them to update immediately, especially for animation, and Fabric ensures that this event runs on the UI thread for instant feedback, while the less critical task like the network response can resume afterwards. So that's where multi-priority scheduling comes in. Another improvement in the new architecture is the turbo modules. So in the old architecture, all the native modules were initialized at app startups. So even the ones that we are not using, they are initialized. So this causes a wasted memory and it slows down the launch time. So what turbo modules does is that it fixes this with lazy loading the modules. So the modules are only loaded when needed. So this reduces startup time, it saves memory by avoiding unnecessary work. So we also have something in the new architecture that we call code gen. So since JavaScript is loosely typed and C++ is a very strongly typed language, so what code gen does is it generates type safe bindings between the JavaScript and the native side, and also generates necessary boilerplate native code for JSI host objects at build time. So this ensures consistency and reducing runtime errors. And that's, my friend, is how React Native works in the new architecture. So let's look at a simple analogy to understand the architectures better. So imagine two chefs, JavaScript and native, each in their own smart kitchen. So they have their own blender, their own microwave, and so on. So they want to cook a meal together, but the problem here is that they speak different languages. In the old system, they relied on a translator for every request, which is a synchronous bridge. So they'll be like, oh, turn on the oven. This will be like start the blender and so on. So the asynchronous bridge, the translator has to translate for each chefs. So this worked fine for small meals, but when the recipes got complex and required many steps at once, the translator slowed them down and things quickly got out of sync. In the new system, the both chefs now share a universal remote that works in both kitchen, which is the JSI, the JavaScript interface. So instead of waiting for translations, either chef can control the other's appliances directly. So you can access the method, access the properties. So this is exactly what JSI enables: direct real-time communication between the JavaScript and the native. And yeah, that's it, my friend. I hope you now know how React Native works and how it evolved from the old architecture to the new architecture. So thank you for watching and see you on the next.